All right, so we're in section 4.2 now. In 4.2, we're introducing the mean value theorem, which is actually one of two existence theorems in this section, and the last two existence theorems that we talk about in Calculus 1. So again, existence theorems are theorems that guarantee the existence of something without necessarily showing you how to find it. In chapter 2, we talked about the intermediate value theorem, which we'll actually use in this section. That's an existence theorem. In the previous section, 4.1, we talked about the extreme value theorem. That is also an existence theorem. And in this section, we're going to talk about two more, Rolle's theorem and the mean value theorem. Rolle's theorem we're going to introduce here, and we're going to look at a couple of little applications of it. Actually, I think one real application of it, but its primary purpose is to show up in the proof of the mean value theorem. The mean value theorem is one of the most important theorems in calculus, and it has a whole lot of really important implications. So Rolle's theorem is sort of setting us up for that. We're not even going to get to the mean value theorem in this video. That'll be part 2. But for now, let's talk about Rolle's theorem. Rolle's theorem says that if f is a function that satisfies 3 hypotheses, 1, f has to be continuous on a closed interval ab. It also needs to be differentiable on the open interval ab, and f of a and f of b need to be equal. So if the endpoints when plugged into our function are giving me the same output, that's this third hypothesis. If all 3 of these are true, then Rolle's theorem says there is always going to exist a number c in the open interval ab such that f prime of c is equal to 0, meaning c is a critical number. Okay, so let's look at some graphical examples of why this might be the case. Here's 4 examples. Notice in each of these examples, if you look at the interval ab, the points that correspond to those endpoints are the exact same height. Here and here, here and here. Okay? What that's telling me is that f of a is equal to f of b in each of these graphs, okay? This one included. Now, Rolle's theorem says that if that's true, that's the third hypothesis, and if the function is continuous, notice all of these functions are continuous on that closed interval, because I can draw each one of them without picking up my pen, and if the function is differentiable on the open interval ab. Remember, you can tell that a graph is differentiable by looking at its graph if it has no discontinuities, which we know it won't because we're assuming it's continuous, and if it doesn't have any sharp corners or cusps anywhere. It's relatively smooth, which is the case for all of these. Notice in all of these cases, we have some point, at least one point, where a horizontal tangent exists. That's what it means for f prime of c to equal 0. Logically, that kind of makes sense, because if you think about this graph, for example, if f of a and f of b are equal to each other, and if the graph starts to move above, like up, if it's increasing away from f of a, then in order for this endpoint f of b to be equal to f of a, the graph eventually has to come back down again. And then because it's differentiable, it's going to do it in a smooth way. And as soon as it changes from increasing to decreasing, that's where that horizontal tangent is going to occur. Similarly, if we decrease away from f of a, we have to then increase up to f of b eventually because they're supposed to be equal, indicating that we'll get a horizontal tangent. If we don't increase or decrease away from f of a, then we have a constant function. And f prime of c is 0, regardless of what c we pick here. F prime of all of the numbers between a and b would be 0 because it's a horizontal line. Graphically, that seems to make sense, but that does not constitute a proof. So what we need to do is prove this, and we look at it in 3 cases, kind of similar to how I just broke it down. So we have 3 possible cases that we're going to look at. If f of x is a constant function. So if f of x is equal to k, meaning a constant function, then f prime of x is equal to 0. That's this case right here, everywhere, right? So c can be any number in the interval ab, and f prime of c is guaranteed to equal 0 because it's true for all numbers in the domain of that function, or at least on the interval ab. So that takes care of case 1. Case 2. Remember, a represents the left endpoint of this function, so that's what I'm looking at when I see this a here. If I can find some x in the interval ab where f of x is greater than f of a, like this function right here, if that's x, then this right here would be f of x, whereas this would be f of a. Notice that f of x is greater than f of a in this case, right? According to the extreme value theorem, which we talked about in the previous section, f has to have a maximum value somewhere in the closed interval AB. Now, why am I able to apply the extreme value theorem? Well, the extreme value theorem is always true if f is continuous on a closed interval AB. But that's one of the assumptions or hypotheses in Rolle's theorem. So we already know that that's in play here. I get to use the extreme value theorem. According to the extreme value theorem, there has to be a maximum value somewhere in that closed interval. But since f of a is equal to f of b, then f of a and f of b are neither of those candidates for the absolute maximum, because we already know by assumption there exists some x in between a and b, so in the open interval ab, that's greater than f of a and thus also greater than f of b. So what does that mean? Well, f has to have a local maximum at c, that value where that absolute maximum is obtained. And because f is differentiable everywhere in the open interval, it has to be differentiable at c, which means that local maximum has to be occurring at a critical number, and not one where f prime is not f prime of c doesn't exist. It would have to be f prime of c equals 0 by Fermat's theorem. Okay, case 3 is similar. I'm not going to read through that one, but this is basically the same idea, except we assume that there exists some f of x less than f of a, and we apply the extreme value theorem again, but this time looking at a minimum value and applying Fermat's theorem again. So this proof establishes Rolle's theorem because it covers all possible cases. Either you have an f of x that's larger than f of a, and f of x that's smaller than f of a, or if neither of those are true, f of x is equal to f of a for all x in the closed interval, making it a constant function. Rolle's theorem is true in all three of those cases. So let's look at an example here. We want to verify that f of x equals x plus 1 over x, we saw this function show up in the previous section, satisfies the hypotheses of Rolle's theorem on the closed interval 1/2, 2, and we want to find all numbers c that are guaranteed by that theorem. Okay? So, first of all, what are the three hypotheses? We want to know if the function is continuous on the closed interval, AB, or in this case, 1/2, 2. We know that both of these functions, x and 1 over x, as a polynomial and a rational function, are continuous on their domains, right? And this has a domain of all real numbers. This has a domain of all real numbers except for 0. So these are continuous on 1/2, 2, because this interval does not contain 0, the only number which would be a problem. So f of x equals x plus 1 over x is continuous on that closed interval as well. And that's because we had a theorem back when we talked about continuity that said the sum of two continuous functions is also continuous. Okay, so we just showed, and notice there's not a big mathematical thing happening here. It's just recognizing where these functions are continuous and then citing a theorem, or just simply saying that the sum must also be continuous. 2, same argument basically, x and 1 over x are differentiable. I'm going to abbreviate that, differentiable on 1/2, 2 by the exact same reasoning. Both of these functions are differentiable. This one is only not differentiable at 0, but that does not show up in this interval. So f of x equals x plus 1 over x is differentiable on 1/2, 2. Okay? And again, that's because the sum of two differentiable functions is also differentiable. That's a theorem that we've also encountered. Finally, Rolle's theorem. Rolle's theorem says, not Rolle's theorem, the third hypothesis says that if I plug in both endpoints of this interval, I get the same number. What is f of 1/2? F of 1/2 is equal to 1/2 plus the reciprocal of 1/2, which is 2. That equals 2.5. What is f of 2? Well, that's equal to 2 plus the reciprocal of 2, 1/2, also 2.5. So, f of 1/2 is equal to f of 2. That's the third hypothesis. Plugging in my endpoints gets me the same number. Okay? I didn't leave myself enough space, so I'll probably do the last part on the back. So what's the last thing that we need to do? We need to find the value c that's guaranteed by Rolle's theorem. That value c is the value within this interval where f prime of c is equal to 0. In other words, I should be able to find a number in here such that f prime of that number equals 0. So let's do that. I think I can actually squeeze this in. It's not going to look very nice, but whatever. F prime of x, we've already found, is equal to 1 minus 1 over x squared. And if you recall in section 4.1, we have solved this before. This implies that x is equal to plus or minus 1 if we solve this equation, okay? But we only care about numbers that are in this interval because that's what Rolle's theorem is saying. There must be a number in this interval, the open interval, 1/2, 2, such that f prime of that number is equal to 0. And positive 1 is that value. So c, the number that we're guaranteed by Rolle's theorem, must be 1. Okay? I'm going to cut this video a little bit short. We're going to look at one more application of Rolle's theorem in the next video, and then we'll use Rolle's theorem to prove the mean value theorem, which will carry us through the rest of this section.